Hello everyone. So in this lecture the implementation of convolution algorithm using fewer number of multiplication operation will be discussed, and that technique is called fast convolution. Okay, so we all know that convolution can be expressed as a matrix multiplication. Okay, so consider a n point sequence given by value h0, h1, h2, hn minus 1. So this is in time domain, and a L point sequence given by x, and the set is x0, x1, x2 to xl minus 1. Now let say that n is equal to 2 and l is equal to 3, so h will become h0 and h1, and x will become x0 and x1 and x2. Okay, so suppose if we want to perform convolution of h and x, so this is equivalent to inverse z transform and multiplication of hz into xz. So convolution in time domain is equivalent to multiplication in z domain. Okay, so I can write h z as h of 0 plus h1 z inverse, and I can write xz as x0 plus x1 z plus x2 z inverse. So hz into xz will be given by h0 into h1 z inverse multiplied by x0 plus x1 z plus x2 z inverse, and if I will expand the brackets, the final result will be h0 x0 plus h0 x1 plus h1 x0 z inverse plus h0 x2 plus h1 x1 z raised to power minus 2 plus h1 x2 z raised to power minus 3. So this is nothing but a polynomial multiplication and addition. Okay, so total multiplication, you can see that here 1 2 3 4 5 6 multiplication, and total number of addition is 1 2 3 and 4 and 5. Total number of addition is 5. So considering the multiplication, which is considered as a complex operation as compared to addition, because it is a kind of shift, add and shift, so hardware corresponding to multiplication operation is very large and complex as compared to the simple adder. Okay, so here multiplication is considered as a strong operation and addition is considered as a weaker operation. Stronger in the sense it will take larger time and more complex hardware is required. It will take less time and can be done using a simple hardware. So total number of multiplication is nothing but L into N. So L was 3 and N was 2, that is 6. Okay, now the concept of fast convolution is to reduce the strong operation like multiplication at the expense of the weaker operation like addition. Okay, so now how multiplication can be reduced at the expense of addition, we will see by taking an example. So consider a complex multiplication. A plus j times b multiplied by c plus j times d, that is equal to E plus j times f. So A plus jb is signal sample and c plus jd is coefficient. Okay, so if we expand this bracket, the result will be AC minus BD plus imaginary part is AD plus BC. Okay, so this multiplication can be expressed in a matrix form. So in matrix form, I can write like this: EF column matrix, the left hand side, and the right hand side this coefficient C minus D from this term, D and plus C from the second term. This is a square matrix, and the remaining term A and B in the form of a column matrix. Okay, so A and B is in this term also and in this term also. I have written this as a column matrix. Okay, so you can verify A into C minus D into B, this term, and for second term A into D and B into C. Okay, so this is valid. So at this point you can see that total number of multiplication operation is 4 and addition operation is, so total addition operation is 1 and 2. Okay, so this is the real part, this is the imaginary part. So 2 operation, this is also a kind of addition. Now this term AC minus BD can be written as A into C minus D plus D into A minus B, and the imaginary term AD plus BC can be written as B into C plus D, D into A minus B. Okay, so E plus GF can be written as A into C minus D plus D into A minus B. This is the real part plus the imaginary part, that is AD plus BC, can be expressed in this form: C plus D plus D into A minus B. So if you look at this term, you can see that the addition, let's say this is addition A1, this is addition A2, and this is addition A3. Okay, we will not consider C minus D or C plus D as addition because C and D are coefficients. So C minus D and C plus D can be pre-computed. Their value is constant, so we can compute C minus D and C plus D before. Okay, and considering multiply operation, so this is, let's say, multiplication M1, this is M2, this is multiplication M3, and this is also multiplication M2. They both are same. So total addition is A1, A2 and A3, that is 3 addition, and total multiplication is M1, M2 and M3. M2 and M3, that is also 3. So in this, total number of multiplication operations were 4 and total number of addition operations were 2, and in this, one multiplication operation is reduced. Now total number of multiplication is 3 and one addition is increased. So one multiplication operation is reduced at the expense of one addition operation, and this will significantly reduce the time and complexity. The multiplication operation takes comparatively larger time as compared to addition operation. So this is the concept, and this thing can be expressed in a matrix form as well in this way. So this term can be written as 1 0 1 0 1 1 and C minus D into A, C plus D into B, and D into A minus B. Okay, so this is the real term, and E is real and F is imaginary. This can be expressed in this form. Further, this matrix consists of the constants multiplied by the signal sample, so we can separate them. So this matrix can be further decomposed in this form in a diagonal matrix, 3 cross 3 diagonal matrix. And 3 cross 1 column matrix. Okay, so this is this term C minus D into A, the second term C plus D into B, and the third term is D into A minus B. And further, this matrix can be decomposed because this consists of signal A, B and their subtraction. Okay, so we can separate the signals individually. So I can write this as 1 0 1 minus 1, and this as simply A and B, and this as it is. like this. So now this consists of only signal A and B. This consists of constants coefficients. Okay, so C minus D, C plus D can be computed before, and this term is responsible for addition A3 because we have A minus B. Okay, so this is addition A3 A minus B. So this matrix is responsible for addition A3. Now this is responsible for multiplication M1, M2 and M3. Okay, so C minus D into A, C plus D into B, and D into A minus B. This is multiplication A1, this is multiplication M3, and this is multiplication M2. And finally this matrix is responsible for addition A1 and A2, that is A1 and A2. So that's why this matrix is known as pre-computation matrix. And finally this matrix will be adding all the computed terms, so this is known as post-computation matrix. Okay, so this 3 multiplication and 3 addition is expressed in matrix form. So architecture complexity is reduced to 3 multiplication and 3 addition from 4 multiplication and 2 addition. Okay, so the final comment: architecture complexity is reduced to 3 multiplication and 3 addition from 4 multiplication and 2 addition, and 1 multiplication operation decreased at the cost of 1 increase in addition operation. So this is the concept of fast convolution that we are going to use. We will try to reduce the multiplication operation. Okay, so this consists of 6 multiplication, this example of convolution, and 5 addition. This operation can be represented in the matrix form, and we will aim to reduce the multiplication operation, and as a result addition operation will increase. Okay, so this is the basic concept of speeding up the convolution operation, and we will start with first Cook-Toombs algorithm, that is based on Lagrange's interpolation, and second is Vinograd algorithm based on Chinese remainder theorem, CRT algorithm. Okay, so those two algorithms will be used to derive the concept of fast convolution.